Hello, I am Professor N.B. Hulle from G.H. Raisoni Institute of Engineering and Technology, and in this video we will learn the concept of or try to understand the concept of dot convention techniques. To begin with, I will start with the basic laws, that is Maxwell's screw rule or the right hand grip rule. I will go through the meaning of both rules are the same, that is Maxwell's screw rule is very same as right hand grip rule. Again, right hand grip rule is divided in maybe available in the two versions. This is the version 1 and this is version 2. Version 1 is applicable to this kind of the arrangement and version 2 is applicable to this kind of the arrangement. I will go through the both. Now here in this case, Maxwell's screw rule, if the right-handed Cork screw is assumed to be held along the conductor and screw is rotated such that it moves in the direction of the current. The direction of the magnetic field is the same as the direction of rotation of screw. It is known as Maxwell's screw rule or right-hand screw rule. Here in this case, I am taking this pen as this particular pen as screw, and if I am rotating this screw in the clockwise direction, the screw is going downward because it is right-handed screw, means the current will be in the downward. In that particular case, the magnetic field will be in clockwise direction. That is the case. Similarly, if I am going for the another example, which is this, that is right-hand grip rule. The point right hand thumb in the direction of the current and then curl your fingers around the wire, then curl finger points to the same direction of the magnetic field around the conductor. Means here, if this is a pen, I am taking it as a screw, and if I am holding this screw something like this and this thumb indicates the direction of the current, and whatever I am holding this curl fingers, these are nothing but the direction of the magnetic field. Means here in this case, if the current is upward, it will be in that is anti-clockwise direction will be the magnetic field. And generally we will use this third concept in case of the coupled coils. Curl your right hand fingers in the direction of the current flowing through the coil and stretch the thumb. The stretched thumb will give the direction of the magnetic field. Here in this case, we are this curl finger will give the direction, of the magnetic field, and this thumb will give the direction of the current. Here is the reverse is the case. These curl fingers will give the direction of the current. In that particular case, this thumb will give the direction of the magnetic field. That is, magnetic field is always from the N pole to the S pole through the magnetic path. Means here this direction will be something like this, that is N to S, because line of fluxes are starting from the that is N pole and it is ending at the S pole, not in the magnet, not something like this, N to S, not something like this. It is through the air path or through the other magnetic path, that is starting from the N and it is ending towards the S. Now here I will start with the concept which we are trying to understand, that is dot conventions, how we are using the dot conventions. For that case, this is the popular example of the 3 coils or sometimes 4 coils be taken to understand the concept of the dot conventions. Here the 3 coils, that is coil A, coil B and coil C, which are wound on the common magnetic circuit. Here this is the coil A, this is the second coil, that is a B, and this is the third coil is the C, having A1, A2 as the terminal, B1, B2 as the terminal, and C1, C2 as the terminal. N is the number of turns of the coil A, that is NB is the number of the mistake is here. This NB is the number of turns of the coil B, and NC is the number of turns of the coil C in this particular case. N is the number of turns of the coil A, B and C and so on. Now here in this case, we are trying to understand the concept of dot, how we are using the dots. Now here in this case, consider that current IA enters at the terminal A1. We are assuming the current enters at the terminal A1, means current is here, and in this case encircle the core, the current encircles the core in the counterclockwise direction. Means again, if I am taking the pen and if I am moving with the direction of the current, look at here, this direction I am rotating, it is anti-clockwise direction. The screw is coming out of the cork out of the cork in the upward direction. That's why in this particular case, the direction of the flux, in this particular case, the direction of the flux is upward. Direction of the flux is upward for the coil A1, for assumption current is flowing from A1 terminal and traveling towards the A2 terminal. Directed upwards means current direction is upward. The flux through the core is directed. Clockwise through the core. Means here, this flux is flowing in this direction. That is nothing but here in this way, which is the clockwise direction. Means this is the flux produced due to the current flowing in coil A from A1 to A2. Now here dot is placed quite arbitrarily at terminal A1, means dot can be placed at A1 or can be A2 initially for the first coil. Then on we cannot make the dot arbitrarily. The dot on the coil B or on the coil C depends on where we are putting the dot in the coil A, maybe at A1 or maybe at A2, that we will see in detail. This can be done for any coil. It can be done for A1, A coil, B coil, or it can be done for the C coil. Once dot is placed in one coil, the dots on the other terminal of the coil, remaining the coils, cannot be placed arbitrarily. Means we cannot put arbitrarily for the B coil or for the C coil. Dots on the other coils are now automatically decided according to the sense of the winding. Means depending on the winding of the B1 or B coil or C coil, its dot will be decided. That may be at B1 terminal or B2, that may be at C1 terminal or maybe at C2 terminal. Now here we have the first dot, which is B1. Now here we have the first dot, which is A1, that already decided its direction of the current. We have assumed this direction, the flux produced due to the coil A, which is something like this. This is the direction of the flux produced in the core due to the current flowing in the coil A, that is from A1 to A2. Now here in this case again I will go through. The position of the dot in the B coil should be such that the current entering into the dot of the B magnetizes the core in the same direction as that of the A. Means here, if we are passing the current from B1, in that case, if the flux is the same direction, if the flux has the same direction as that of the direction of the flux produced due to the A coil, when we are putting or we are passing the current from the A1 coil. If we are passing the current from the B2, in that particular case, if the direction is downward, then that dot may be at B1 or B2, that we will see. If the dot is placed at B2, what is our first assumption? We are putting the dot at B position. Suppose dot is placed here. The current entering this terminal will encircle the core in the counterclockwise direction. Means here, if I am taking this pen, and if the current is passing from the B2, in that particular case, the current will encircle something like this, that is counterclockwise. In that case, the pen or the screw is coming out of the cork. In that particular case, the direction of the flux will be upward, which is opposite to that of the direction of the flux produced by A coil by putting at the dot at A1. That is, current is passing from A1. That's why we cannot put dot at B2. Because if we are putting the dot at B2, means indirectly we are assuming that current is entering from the B2. And in that case, the flux is not supporting to the flux produced by the coil A. That's why its dot cannot be here. Now I will start with the similar assumptions here. Assumption is that current is flowing in this direction. The flux, it is upward. Here it is horizontally. This is downward. And this is again horizontal, and this is the flux produced by a coil whenever current is entering at the A1 terminal. Now we will assume that if the current is entering at the B1 terminal, now look at, again I am taking the pen here, if the current is at B1, in that particular case, now look at the direction of the current is flowing in this direction, that is B1 direction, and if I am rotating the pen in that particular direction, which is a clockwise direction, in that case the pen is going down or screw is going down. Means here in this case, if I am assuming the direction of the current here, it is incoming, at B1 terminal, in that particular case, the direction of the flux produced by that current will be the downward. And this direction is very same as the direction of the flux which is of the coil A when putting at the dot A1. Here in this case, the dot must be placed at B1 rather than placing at A1. Now here, if the dot is placed at B1, the current is entering at this terminal, will encircle the core in the clockwise. According to the corkscrew rule, the flux is directed downwards, that is downwards, and the flux produced will be the additive, so that the flux produced by the current IA, so that the dot should be placed at the B1 location. Means it is supporting to that particular current. That's why if we are putting the dot at A1, for the coil B, dot should be at B1 and it should not be at B2, because B2 current or current entering from the B2 will create the flux opposite to that of the current created by putting the dot at A1. That's it. Now here, if I am moving towards the third example, or where should be the dot of the coil number third, that is coil C. In this particular case, similarly for the coil C, dot is placed at C1. Now here the current entering, now look at here, again I am taking the example of the pen here. I am holding this pen horizontally because the coil C is horizontal coil. Now here in this case, if I am rotating the coil in this direction, because coil is moving in that particular direction. In this direction, coil is moving in this direction. Now here in that particular case, coil is moving in this direction. In that case, if I am rotating this coil, the screw is coming out of the cork. The screw is coming out of the cork. Means here in that case, if I am traveling with the direction of the current, means something like this. If I am traveling something like this, in that particular case, if I am rotating the right-handed screw, in that particular case, the screw will come out. Means this will be the direction of the flux. That's why, and here, now I will try to conclude here. In this particular case, now here, if the current is entering here in the coil A, in that case the flux will be upward, it will be horizontal, it will be downward here, and it will be horizontal something here. These are the directions of the current. Now here similarly, if we are passing the current from B1 here, in that case the flux will be downward in this direction, it will be horizontal in this direction, it will be upward in this direction, and again it will be horizontally. Now here similarly, if we are looking for the coil number C, that is a third coil, in that case if the current is entering in C1, in that particular case the screw will come out, because it is right-handed screw. In that case the direction of the flux for the coil C, whenever current is entering at the C1, will be something like this. It is upward, and it is horizontal, it is downward, and finally it is backward. Now look at here, what do you mean by the dot techniques? Means whenever we are putting the dot at A1, the flux produced will support whenever current is entering at the B1, and similarly it will support whenever current entering at C1. In other way, we can put the dot at A2, C2 and B2. In that particular case, again it is also supporting. Means we have to put the dot in such a way that the flux will be additive. And if we are putting the dot at the opposite place, means the current is not supporting, and at that place expected that dot should not be placed at that particular terminal. We have seen how to calculate or how to put the dot in the coil corresponding to the addition of the flux in both cases. Now here we will try to understand the sign conventions for the mutually induced EMF. Here, in this case, if current is entering at the dotted end in one coil, then the reference polarity of the mutually induced EMF in other coil is positive at the dotted end. Means what? Now here, in this case, if the current is entering at the dotted end in this particular coil, in that case, induced EMF has a positive polarity at the dotted end and opposite is the negative polarity. Now here in this case also, here is a dot and here is a dot. In this case again look at the I1, the current is entering into the dot. In this case the induced EMF has positive polarity at the dotted end and negative polarity at the other side. Similarly, if I am assuming the second coil here, if it is excited from here, current is entering into this coil at the dotted end. In that case, the mutually induced EMF will be dotted, it's positive at the dotted end and negative at the far end. Similarly, in this case, if I am assuming the current is entering at this dotted end in the coil B, in that case, induced EMF has a positive polarity at the dotted end and negative polarity at the far end. These are the sign conventions for the current entering into the coil. Similar things are available for current exit from the dotted end. This is another case. If the current leaves the dotted end of the coil or one coil, the reference polarity of the mutual induced EMF in the other coil is a negative at the dotted end. Means here, in this case, what we are assuming, the current is leaving the dot. In previous case, we are assuming the current is entering into that. Here, current is leaving the dot. If the current is leaving the dot, then mutually induced the EMF has negative polarity at the dotted end and positive polarity at the far end. Positive polarity at the far end. Similarly, in this case also, current is leaving this dot. Here, in that case, the negative polarity will be at dotted end and the positive polarity will be at far end. This will be the polarity of the induced EMF. I will consider the other case. Here in this case, the current in the coil B leaves the dot. Means in that case, induced EMF will be negative at the dotted end and positive at the far end. Similarly, here also the current leaving the dot at the coil B, in that case mutually induced EMF will be negative at the dotted end and positive at the far end. These are the standard sign conventions for the dot convention techniques or sign conventions for the mutually induced EMF in case of the dot convention techniques. Here I have some examples here. In case of the dot convention, simple example here. In this case, this is dotted end and current I1 is entering into the dotted end. This current I1 is entering into the dotted end. Means in this case, the mutually induced EMF will be positive at the dotted end and negative at the far end. But this polarity will be taken with reference to this V2. V2 is generally positive here and this V2 is negative here. This positive sign is same as this. This positive sign is same as this. That's why this voltage V2 is positive, which I have written the same thing here. I will read out. The sign of the mutually induced EMF V2 is determined by the reference polarity for the V2 and the direction of the current I1. Since I1 enters the dotted end of the coil 1, V2 will be positive at the dotted terminal of the coil 2. Which will be positive here. Now the mutually induced EMF will be V2 is equal to M into di by dt. That is the formula for the mutually induced EMF in the second coil. Similarly, if I am going for another example here, in this case current enters at the dotted end again, but the dot is at the second portion. Now here, as per the entering dot technique, that particular rule, if the current is entering into the dot of one coil, mutually induced EMF will be positive at the dotted end and negative at the far end. Now here in this case, why the sign is a minus? Because the polarity of the voltage V2 is here is a plus and here is a minus, that is a routine polarity. Induced EMF has a polarity opposite to that of the routine polarity. That's why its sign is a minus. Now here current I1 enters the dotted terminal of the coil 1 and V2 is a positive at the dotted terminal of the coil 2. Means it will be positive here and negative will be on other side. That's why mutually induced EMF will be negative with respect to the reference polarity of the V2 as given below. That is V2 is equal to minus M into di1 upon dt. That is nothing but the mutually induced EMF in this particular example. Now here I will take another example here. Now here in this case what I am assuming, the current is flowing in this coil B, if the current is flowing in the coil B and the current is coming out of the dot, the current is coming out of the dot, in that particular case, induced EMF will be negative at the dotted end and positive at the far end. And this polarity is matching to this polarity of the reference polarity of the V1. That's why this particular voltage is the positive. Means current I2 leaves the dotted end terminal of the coil 2, then V1 is a negative at the dotted end and it is opposite at the far end, and that's why the mutual induced EMF with respect to the reference polarity of the V1 is same as V1 is equal to M into di2 upon dt will be the mutual induced EMF in the coil number 1 when the current is changing in the, that is coil number 2, that is coil B. Here this is last example of this category. Now here if the current is coming out of the dot in the second coil, in that particular case what the rule says, the induced EMF will be negative at the dotted end and which is positive at the far end. This polarity is other than or opposite to that of the reference polarity. That's why the sign is the minus sign. Means we have the two basic rules for the dot convention technique. These dots are always available on the coil in the given circuit. What we have to calculate? We have to find out the polarity of the induced EMF. The polarity of the induced EMF depends on whether the current is entering into the dot or current is leaving the dot. If the current is entering into the dot, in that particular case, the polarity of the induced voltage will be positive at the dotted end. And if the current is leaving the dot, in that particular case, polarity of the induced EMF will be negative at the dotted end. Now here I will take one simple example here in this particular case, that is calculation of the total inductance of the coil when the two inductances are connected in series. Here is one dot is available here and other dot is available here. Means the fluxes of both coils are additive because the dots are in that particular fashion. If the dots are in opposite direction, in that case fluxes may be subtractive. Now here we are interested to find out how much is the total inductance, that is the combination of the self-induced self-inductance and mutual inductance. The total inductance we are interested in the calculation. Now we will apply the KVL here. Here in this particular case we are assuming this is as a current I, and depending on the assumed direction of the current we will mark the polarity. Here this will be the plus, this will be the minus, here this is the plus and this will be the minus for self-induced EMF, that is polarity of the self-induced EMF, and then we will see the polarity of the mutually induced EMF. Now here in this particular case, if we are interested in the calculation of the polarity of the mutually induced EMF for coil 1 and for coil 2. Now here in this case, if current is entering into dot in this coil, because direction of the current is a forward, means in both coils the current is entering into the dot. In that particular case, mutually induced EMF will be positive at the dotted end and negative at the far end for the first coil. Similarly, in the first coil current is entering into the dot, that's why mutually induced EMF will be the positive at the dotted end and negative at the far end. Means if we are looking for the polarity of the mutually induced EMF here, then we have to look at the current entering into the dot or leaving the dot in the second coil. In this case the current is entering into the dot in the second coil, that's why mutually induced EMF will be positive here and negative here. And for marking the polarity of the mutually induced EMF in this particular case, we are looking at here the current is entering into the dot in the first coil, that's why the mutually induced EMF is positive at the dotted end and negative at the far end. Now we are applying the KVL. We are traveling from this terminal, that is a negative to positive, which is a plus Vs. Then we are traveling from this sign is equal to, then we are traveling from positive to negative for self-induced EMF. That's why it is a minus. This is minus L1 into di by dt. Then for mutually induced EMF, that is positive to negative, which is minus M into di by dt, because current in the first coil is very same as the current in the second coil. That's why it is di by dt. Then for self-induced EMF, that is positive to negative again, which is minus here. This minus L2 into di by dt, which is self-induced EMF. Then again here it is a positive to negative. For this polarity it is positive to negative. We are moving in this direction, positive to negative, that is minus, that is M into di by dt, because M into di by dt is mutual induced EMF. For this coil is same as this particular coil, because here is mutual inductance in this particular case mutual inductance is M. That's why its mutual induced EMF will be M into di by dt, and its mutual induced EMF again is M into di by dt. We are interested in the polarity here itself. Now, if we are simplifying this equation, this Vs is equal to, we are shifting this all the terms on the next side, this will become plus 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 and so on. If I am taking this as summation, that is di by dt, then Vs is equal to, it is L1 plus L2, this M plus M will be the 2M, and I am naming this equation as equation number 1. Similarly, if its total inductance is L, in that case, this applied voltage will develop some voltage or across this particular case, that is L equivalent into di by dt. And if we are comparing these equations here, look at here, this L equivalent, I have written something here, that is series additive. Whenever dot is, one dot is here and other dot is here, in that particular case L1 plus L2 plus 2M will be the value of the mutually induced EMF in case, total inductance of when the two coils are connected in series additive. Now here I will go for another example here. In this particular case, one dot is here and other dot is here. Means if we are putting the dot here, in that case the fluxes will be the opposite. That's why the dots are already available with us, which is one dot is here and other is here. Now I will assume this direction of the current. We will try to apply the KVL here. If this is the direction of the current, in that case this is the polarity of the self-induced EMF in the coil number 1. This is the polarity of the self-induced EMF in the coil number 2, that is B coil. Here, this will be L into di by dt. This is this value, self-induced EMF, L1 into di by dt. Its self-induced EMF will be L2 into di by dt. Now here, look at, current is entering into the dot of the coil number 1. Current is entering into the dot of the coil number 1. Then, the polarity of the induced EMF will be positive at the dotted end. Means here it will be plus polarity and it will be minus polarity for mutually induced EMF in other coil. Current in this coil, polarity in this coil. Now look at for this coil. For this coil, the current is traveling in this direction, means current is leaving the dot. Current is leaving the dot. In that particular case, induced EMF will be negative at the dotted end and positive at the far end. Means this green polarities are the polarities for mutually induced EMF, and this blue polarities are the polarities for the self-induced EMF. Now here, if I am applying the KVL to this loop, and if I am traveling in the clockwise direction, we are traveling from the negative to positive, which is a plus Vs. Then for self-induced EMF, positive to negative, which is minus L into L1 into di by dt. Then for mutually induced EMF of the coil number 1, that is negative to positive, which is a plus, that is M into di by dt. For self-induced EMF, positive to negative, which is minus L into L2 into di by dt. For mutual induced EMF of the second coil, that is a negative to positive, which is a plus, that is M into di by dt. If we are simplifying this equation mathematically, all these terms are shifted on the next side. It will become, there is a plus, this term will become minus, this term will become plus, this term will become minus. And if we are taking di by dt as a common, in that particular case, L1 minus M, L2 minus M. And if we are taking this total value, then it will be, that is L1 plus L2 minus 2M di by dt. And if it is a total inductance, in that particular case, this is the equation number 1 and it is the equation number 2. If we are comparing the both equations, in that particular case, we are able to have the complete or total inductance of this coil in this particular case, and which is, if we are comparing both equations, this will be the final solution here. In this case, the equivalent inductance in series opposing case will be L1 plus L2 minus 2M will be the total inductance when coils are connected in series opposing.